Actually, this video didn't originally, the original one didn't show the writing. So 0.5 is the equilibrium constant. They gave us the equilibrium concentration, so it's just in writing the expression for Kc. What does the 0.5 mean now?
Equilibrium lies to the left.
The equilibrium lies to the left.
Ma'am, it says at the top, specific temperature, does that mean constant temperature?
It means a constant temperature, and the volume will also be constant.
No, that's...
Okay, wow.
Oh, ma'am. That makes it the same.
Okay, so what do they give us? They give us the Kc value, am I right? Talk to me.
They give us the
They give us Kc's value is 4. And they give us equilibrium concentration.
Yes, ma'am.
So they give us at equilibrium. So at equilibrium, what do they give us? Help me please. The concentration of sulfur dioxide is
0.2.
0.2
Yes, ma'am.
mole per cubic decimeter. And the concentration of NO2? 0.1 mole per cubic decimeter. And the concentration of NO, nitrogen monoxide?
That's 0.4.
0.4 mole per cubic decimeter. And the concentration of sulfur trioxide?
It's unknown.
Okay, so what I'm going to do, in mathematics, if something is unknown, I can say it's X. Okay. And I guess now that they're asking us to get X.
Yes,
ma'am.
So the first thing we need to do is to get the correct expression for Kc. So it's concentration of SO3 times concentration of NO. Is the equation balanced, by the way?
The mole ratio is 1 to 1 to 1 to 1.
There's no... It's balanced, ma'am. Yes,
Okay.
oxygen is balanced.
And then it's on the concentration of SO2 times the concentration of NO2. Oh, so there are no like powers here, but for 1. So x4 equals x times 0.4 divided by
0.4.
You start from the divide from this way.
0.2 times 0.1. So x would be equal to
0.2.
4 times 0.02, am I right?
Yes, ma'am.
Divided by 0.4, which gives us
0.2.
0.2 mole
Look at that.
per cubic decimeter. Nice. Good. So it was still not unmanageable.
Yeah.
Okay.
Yes, ma'am.
Okay.
No.
I'm going to work together on it. They say, they say 1 times 10 to the minus 3 moles per cubic decimeter H2 gas and 2 times 10 to the minus 3 moles per cubic decimeter I2 gas was initially mixed in a closed container. Alright, so this is what they give us at the start. And they give me in concentrations, so 1, can I just write times 10 to the minus 3? Or
Yes.
10 to the minus 3?
Yes.
10 to the minus 3
Yes.
mole per
This.
cubic decimeter of hydrogen, and twice 10 to the minus 3 mole per cubic decimeter of the iodine. How much hydrogen iodide will we start off with? Nothing. Nothing. Okay. When the equilibrium mixture is analyzed, it shows the equilibrium concentration of HI is 1.87 times 10 to the minus 3 mole per cubic decimeter. So I need to skip the used formed step. I need to leave a line for this. Okay? And write at equilibrium. Okay, so at equilibrium, the HI concentration is 1.87 times 10 to the minus 3 mole per cubic decimeter. Alright. What do I know about the volume?
Isn't it constant?
The volume would be constant. Then the concentration is directly proportional to the moles. Are you fine with me saying that?
Yeah.
Because concentration is mole divided by volume. That's the equation.
Oh yes.
Because they gave me concentrations to work with, I'm hesitant to use the mole ratio, because the mole ratio says 1 mole of this will react to 1 mole of that and give 2 moles of that. But now that I understand concentration is directly proportional to the mole, I can now say, if this is at equilibrium, how much was formed? How much of this was formed? So go one step back. What is the concentration of the HI that was formed? 1,87 times 10 to the minus 3 mole per cubic decimeter. Are you following? How much of that used, that used how much of this?
935 times 10 to the negative 6. Then you have different standard forms.
Oh, scientific notation.
Yes. But it's 0,000.
Okay, so it's 9,35
Yeah.
times 10 to the minus 4 mole per cubic decimeter. Just check me, please. Yes, of course you can.
Can I write it as like a full number?
Like you want to have lots of zeros.
0,00, you're going to take up space. That's why we have scientific notation.
I'm going to take a
And how much hydrogen would be used?
It would be the same number.
The ratio is 1 mole to 1 mole, so 9.35 times 10 to the minus 4 mole per cubic decimeter. Sorry, I'm squashing it. Give yourself space when you do these calculations. Alright, so what will be left at equilibrium? How much of the hydrogen would be at equilibrium? So you've got 10 to the power minus 3 minus 9.35 exp minus 4. I get horrible 6,5 times 10 to the minus 5.
Yes, that's also. I get
6,5 times 10 to the minus 5 mole per cubic decimeter.
I get 65 times 10 to the minus 6.
Yeah, right. If you want to work with all those, you're welcome. And the second one, the iodine, so it is twice 10 to the power negative 3 minus the 9.35 exp negative 4. So I get 1.065 times 10 to the minus 3. 1.065 times 10 to the minus 3 mole per cubic decimeter. Are you tired, Sandy? Are you alright?
Yeah.
Alright, so now we have the equilibrium concentrations. We need to get Kc's value. To get Kc's value, I need the equilibrium expression for this reaction. So what is it? Kc equals to the power 2, yes.
The hydrogen times the iodine. So now,
Yes.
for this, what were we doing? We're calculating the concentration of the HI.
Yeah. The equilibrium concentration of the HI was given. This part was given. So I need to get to the equilibrium concentration of the hydrogen and the iodine to be able to do the calculation.
Oh, the 1,8 is the it's in equilibrium.
That is the concentration of the HI at equilibrium, yes. 1,87 times 10 to the minus 3 mole per cubic decimeter. So we have to work backwards. Okay, so this becomes 1.87 10 to the power minus 3 squared divided by 6.5 times 10 to the minus 5 times 1.065 times 10 to the minus 3. We need to Cassiopeia that.
50, come on, 4. Come on, 5, 1.
I'll also get that. 10,000.
This is a rounding error.
$50.51. I'm sure I had a similar answer earlier. 50.51. What does this value mean? Equilibrium lies to the right.
Ma'am,
Yes.
I'm still stuck at the, okay, ma'am, they told us that the new equilibrium that HI formed is 1,87 times 10 to the power of negative 3, right? So now, ma'am, to work backwards, so I divide that by 2 to get my iodine and hydrogen.
Yes, because the mole ratio is 2 to 1. See, I went back. This was at equilibrium, so how much was formed? That same amount had to be formed there. And then we divide by 2. According to the mole ratio, they react 1 to 2. And then what you do, this was the used amount of iodine. So what they start off with, 2 times 10 to the minus 3, you subtract this to get this value. That value, you subtract this value that was used from what was given at the start to get that value. Good. The next paragraph is about reaction quotient. It's not in the syllabus anymore, but they don't call it reaction quotient, but they can ask you to determine whether the reaction is at equilibrium. So then they give you the Kc value, they give you concentrations, and they ask you to find out whether the reaction is at equilibrium. If your Kc then is the value that they've given you at the start, using the concentrations, then you know it's at equilibrium. If not, then the reaction isn't at equilibrium. Okay, so we'll do that example 1 there. That will make it clearer, I hope. The Kc for preparation of ammonia from hydrogen and nitrogen at 472 degrees Celsius is 0.105. It was found that the reaction mixture in a 1 cubic decimeter container contained 2 moles of ammonia and 2 moles of hydrogen and 1 mole of nitrogen. So this is the situation. Has the reaction reached equilibrium is the question. So we need to change we need to act as though this would be the equilibrium moles, change them to concentrations. So because the volume is 1, the mole to volume ratio would be 2 mole per cubic decimeter, 1 mole per cubic decimeter, and 2 moles per cubic decimeter.
Is that given the first one?
These values are given and they ask us to determine whether equilibrium has been reached. So I'm acting as though equilibrium is reached just to see if my Kc will be 0.105. Okay, so it is the concentration of NH3 to the power 2 divided by concentration of N2 times the concentration of H2 to the power is a 3. Okay, so it's 2 squared divided by 1 times 2 cubed. This seems so familiar. 0.5. Has equilibrium been reached? No, equilibrium was not reached. And in which direction must the equilibrium shift to reach equilibrium?
To the left.
Must the reaction shift?
To the left.
It must make, you see this Kc value is very small. Much smaller than this one. Okay? So it's too big. It's lying too far to the right, so the equilibrium must shift. So it's not in equilibrium yet. The reaction to the left must be favored. Maybe that's a better way of saying it. The equilibrium will, to reach equilibrium, the reaction to the left must take place. To reach equilibrium, the reaction must favor the system must favor the reaction to the left.
Would it be a reverse reaction?
Yes. All right. Now we can go to the mathematical challenges. Yeah? A mixture of 0.25 mole NO and 0.1 mole bromine is placed into a 250 cubic centimeter container. So the volume of the container is 0.25 mole per, cubic decimeter. 0.25 cubic decimeter, and sealed off at a temperature of 400 Kelvin. Okay. The balance equation for the reaction is given, and it gives us a mole ratio of 2 moles to 1 mole to 2 moles. Obviously, the given amounts will not follow the mole ratio. Okay? Equilibrium is reached after 10 minutes, and it is found that there are 0.2 mole NO present. So 0.2 mole of the NO is present at the equilibrium. Calculate the equilibrium constant at this temperature, it says. So that's what they give us. We need to change the mole to volume, to concentration. But first of all, we need to work back from this. How much of the nitrogen monoxide was used?
0.05.
So 0.05 moles was used. Okay? How much of the bromine would have been used? Here, to do that calculation, I need this ratio. What must I do? Divide by 2. So if I divide that by 2, I'll get 0.025. 25. Just check your zeros, because 2 goes into 5 2 times, and then so 0.025. Are you alright with that?
Yes,
That was used. So how much of the bromine that we started off with will be left at equilibrium?
0.0.
Okay, and how much of the NOBR would be formed?
0.025. Oh, sorry,
0.05.
0.05 mole would be formed. We started off with 0 moles of that, so at equilibrium 0.05 mole will be present. So we've got our equilibrium moles. Can we get our equilibrium concentration?
Yes,
So concentration is mole divided by volume. So here I need to divide by 0.25, and we get
0.8.
and here we need to divide by 0.25, and we'll get
0.3.
and here we have to divide by 0.25. What do we get?
0.2.
And now we are left to write the expression for Kc, which is concentration NOBr to the power 2 divided by concentration NO to the power 2 times concentration Br2. It is 0.2 squared divided by 0.8 squared times 0.3. What do we get this to be?
0.21.
Please use your Casio. Don't just copy. Go through the motion. They give us
0.4 moles given of H2.
0.4 moles of that. Is that all they give us?
Kc equals to 6 times 6.8.
Kc, they say, is
6.8 times
6.8 times 10 to the power
10,
negative 2. Okay. So if I've got the expression for Kc, maybe I can get somewhere. So Kc's expression is the concentration of H2S divided by the concentration of H2. So I know what to work with. This one, sulfur, is not going to affect my equilibrium.
It's in excess.
Okay. Because it is a solid.
They gave us volume as well.
Did they give us volume? What is the volume?
It's 2.
2 cubic decimeters.
Yes, ma'am.
Okay.
Temperature.
Temperature?
Constant.
Sorry?
It's constant, but it's
It is like a 60 Kelvin.
60 Kelvin.
360.
360 Kelvin. So it's constant.
yes.
So there will be an equilibrium reached. All right. Is that all they give us?
Yeah.
Sure. The mole ratio is 1 mole to 1 mole. Now in maths, if you don't know what is used or formed, you change it into an X. Okay? X is a variable. So let's say X moles of H2 was used. Yes.
Ma'am, how can I write in a mole ratio for the sulfur?
Because it's a solid and
Oh,
solids
okay.
do not affect the equilibrium. Okay. How much of this would be left at equilibrium?
0.4 minus X.
0.4 minus X mole. Okay. If that is the case, X mole is used there, how much of this will form?
X.
How much will there be at equilibrium?
Why?
Because what is formed is also going to be what is at equilibrium. All the ones that we've worked with so far. If they give you this amount at equilibrium, it means that amount was formed during the equilibrium reversible reaction. Okay? I think we have one variable and we have two expressions and a Kc. All we need to do is change the moles into concentration. That's the tricky part. So change the mole into concentration. So this one would be 0.4 0.4 minus x over 2. And that one will be x over 2. That is the equilibrium concentration. I think the 2 will sort itself out when I put it into the Kc expression, because 6,8 times 10 to the minus 2 would be x over 2 over 0.4 minus x over 2, and I think those two 2's will cancel. Is my mathematics correct?
Yes, ma'am.
So technically speaking, I'm going to go and I'm going to write this here. 6.8 times 10 to the power minus 2 equals x over 0.4 minus x. Now you need to do your mathematics. So this is 6.8 times 10 to the minus 2 times 0.4 minus 6.8 times 10 to the minus 2 x equals x. Let me just write it better here. So my video candidates can't see. So it is 6.8 times 10 to the minus 2 times 0.4 minus 6.8 times 10 to the minus 2x, and that is equal to x. It's x over 2 divided by, will this not change to x over 2 times 2 over 0.4 minus x? So this 2 cancels that 2.
That's what
Right. Fortunately, you don't have any squares in here, so we don't have to do quadratic solution. All I have to do is say that this plus this times x is this. So it's 6.8 10 to the minus 2 times 0.4. Am I right? So it's 0.0272. This part is 0.0272. And I'll keep all my decimals here because these values are very small. And that becomes, what is it? 6.8 times 10 to the power minus 2 plus 1.
Yes.
That gives me 1.068. 1.068x. Huh? So what is the value of the x? The value of the x would be the 0.0272 divided by the 1.068. What's that?
Zero point zero two five.
0.025.
Yes, ma'am.
Sorry. So,
You could go for another 5 after that. So what is x? X is
So now we have
the
to sub in.
mole. Hmm?
that's
I
it.
never won.
Yeah.
Here's my answer.
Ja, maar in de wel met one now.
Where did you see one? That's a column.
Oh,
Anyways, do you have to start back in?
Yes, because this is the equilibrium concentration. So we've got the X value, so the equilibrium concentration of the H2S is 0.0255 divided by 2, which is 0.01275 mole. Don't drop the unit, please, per cubic decimeter. This was mole. The value of X is the mole, and they required you to get the concentration. Right, I think that's enough for today.